In a twist straight out of science fiction, an anonymous ethical hacker has come forward with claims that Google's quantum computer, Sycamore, may be doing something no one thought possible: communicating with multiple universes. If true, this revelation could shatter our understanding of existence, blurring the lines between science, philosophy, and the fantastical. Could quantum computing, often hailed as the next technological frontier, also be humanity's first real step into the multiverse? The dawn of quantum power. Quantum computing stands at the frontier of modern science, promising to surpass even the transformative impact of digital technology. Traditional computers, which rely on bits to process information, ushered in an era of global connectivity, data analytics, and advanced automation. Yet quantum computers have the potential to go further by tackling problems that current machines cannot handle within any reasonable time frame. This technology harnesses properties from the realm of quantum mechanics, including superposition and entanglement, concepts that defy our everyday understanding of reality. Unlike regular computers that see data in a strict pattern of zeros and ones, quantum systems can explore vast numbers of possibilities at the same time. This advantage opens the door to breakthroughs in fields such as cryptography, drug discovery, and materials science. Researchers across the globe are racing to refine quantum hardware and develop algorithms that can handle real-world challenges. One major goal is to produce machines capable of stable, error-free operations over extended periods. Although quantum computers have shown impressive results in controlled experiments, achieving consistent performance in practical settings is still a work in progress. One of the most striking aspects of quantum computing is its potential to question our assumptions about nature itself. The quantum world is full of puzzling phenomena, such as particles existing in multiple states at once, or influencing one another across great distances. By building machines that exploit these behaviors, scientists hope to better understand the very fabric of existence. Quantum computers may clarify how certain processes work on a microscopic scale, beyond the reach of classical computing. Another area of promise lies in big data analytics. Quantum algorithms could analyze massive datasets for patterns that cannot be detected with standard methods. This might improve weather forecasting, optimize supply chains, or enhance machine learning techniques. The speed and efficiency gained through quantum computing might also reduce energy use across computing infrastructure, potentially cutting costs and lessening the environmental impact. All these possibilities mark a new dawn in computing history. Quantum computers are not just faster machines. They embody a fresh way of thinking about information and calculation. Their emergence highlights humanity's ability to push scientific boundaries and adapt to technologies that challenge our very sense of reality. Beyond binary, the magic of qubits. At the heart of quantum computing lies the qubit, a quantum bit that breaks free from the constraints of classical systems. In a traditional computer, bits can only be in one of two states, 0 or 1. Everything from streaming videos to running complex simulations relies on these two symbols. A qubit, however, can exist in a superposition of both 0 and 1 simultaneously. This peculiar state is what grants quantum computers a massive leap in processing power. To illustrate, imagine trying to find one correct path in a maze. A classical computer tests each potential route step by step, sorting through possibilities one by one. A quantum computer, by contrast, can examine multiple pathways at once. This efficiency arises from superposition, letting qubits act like parallel explorers of the computational search space. When many qubits work in unison, they can process an astronomical number of outcomes all at the same time. Another magic trick of qubits is entanglement, where two or more qubits become linked so that measuring one instantly impacts the others. This linkage remains strong no matter the physical distance between them. When applied effectively, entanglement adds yet another layer of computational advantage, allowing certain operations to be performed with fewer steps or resources than would be needed on a classical machine. Building functional qubits involves overcoming numerous engineering barriers. They are highly sensitive to disturbances from their environment, including temperature changes, electromagnetic fields, or even slight vibrations. Such disturbances can knock qubits out of superposition, causing a loss of information known as decoherence. To address this challenge, Scientists develop elaborate cooling systems and error correction protocols to preserve the delicate quantum states. Many quantum devices use superconducting circuits, trapped ions, or photonic systems to hold and manipulate qubits. Each approach has its own strengths and drawbacks, and researchers have yet to decide which will dominate in the long run. Despite these uncertainties, progress has been rapid. Companies and laboratories worldwide are now experimenting with different architectures for creating reliable qubits. While still in the early stages, the magic of qubits is already reshaping our vision of what computers can do. They hold the promise of simulating intricate chemical processes, cracking advanced encryption systems, and unlocking corners of mathematics once deemed out of reach. As we refine our ability to manipulate these tiny quantum units, we edge ever closer to understanding and harnessing the mind-bending power lurking beneath our everyday reality. A glimpse of quantum supremacy. In 2019, Google's quantum processor, Sycamore, achieved a major milestone known as quantum supremacy. This term refers to the ability of a quantum computer to solve a specific problem so quickly that no classical system can realistically match its speed. For Sycamore, the task was to generate and verify a sequence of random numbers. While that might sound trivial, the time difference was astonishing. Around 200 seconds on Sycamore versus thousands of years on the most advanced supercomputer. This demonstration was not just a proof of technical prowess. It was proof that quantum computation is more than an academic idea. Sycamore showed that these machines can outperform classical computers for at least one carefully chosen test. Though the problem it solved might not have broad practical use, this event ignited enthusiasm and debate. Some argued that the benchmark problem was too specialized, while others viewed it as a genuine step toward real-world applications. Regardless of how one interprets the experiment, Sycamore's success accelerated research across the field. More companies and research institutions poured resources into developing better algorithms, superior hardware, and robust error correction schemes. Collaborations bloomed among computer scientists, physicists, and mathematicians to uncover problems that quantum computers could soon approach. Sycamore's design relies on superconducting qubits arranged in a two-dimensional grid, enabling them to interact in ways that speed up certain operations. Cooling systems keep the processor at extremely low temperatures, reducing unwanted noise that could disrupt the qubits. By carefully calibrating these interactions, Google's team performed a large calculation that classical computers found nearly impossible to mimic in a short time frame. Quantum supremacy, while a fascinating benchmark, is only the beginning. The ultimate goal is quantum advantage, which means handling tasks that have real-world importance, such as drug design, evidence-based medicine, or enhanced cryptography. Scientists want quantum machines that can work on everyday data and deliver breakthroughs that would be otherwise unattainable. Quantum mechanics and the multiverse. The strangeness of quantum mechanics has led to many theories about the underlying structure of reality. One of the most fascinating is the idea of the multiverse. Multiple universes that exist alongside our own. In some interpretations of quantum theory, every time a quantum event occurs, reality branches, creating many versions of what could happen. Though it sounds like fantasy, this concept has found a serious footing among some physicists who see it as a solution to the bewildering behaviors of particles at the quantum scale. Superposition, a key principle of quantum computing, ties back to this theory. When a qubit is in a superposition, it can be considered as exploring multiple states at once, reminiscent of the way the multiverse concept allows for multiple realities. Though this does not mean the qubit lives in a separate universe, it serves as a reminder that quantum systems often defy our usual expectations. Looking at the universe through this lens, each measurement or choice we make might correspond to a split in reality, with all outcomes playing out somewhere in the vast multiverse. This idea has sparked debates in science and philosophy, as it could redefine questions about fate, free will, and the nature of existence. For many people, the notion that countless alternate versions of ourselves could exist is both thrilling and unsettling. Quantum computers, by harnessing strange phenomena like entanglement, may someday offer insights into whether these parallel realities have a basis in fact. If new experiments or advanced simulations point toward interactions that cannot be explained by our current physics, the multiverse idea may gain further traction. This shift would challenge not just scientists, but also society at large. A confirmed multiverse would raise questions about identity, ethics, and how we define reality itself. Quantum computers. As gateways building on the multiverse idea, some have speculated that quantum computers could one day serve as portals for communication with parallel realities. This scenario might sound like science fiction, yet it follows from the peculiar properties of quantum systems. If entangled qubits can affect each other instantly across space, could advanced setups detect signals from different universes? The concept hinges on the possibility that quantum computing processes might reveal patterns unexplainable by ordinary means. A quantum machine could, in theory, pick up subtle cues hinting at phenomena outside our accepted model of the universe. These cues might be anomalies in calculations, unexplained fluctuations in outcomes, or correlations that defy known physics. Supporters of this view claim that if the multiverse is real, there might be ways to send and receive information across the boundaries separating each reality. This speculation often goes hand in hand with ideas about advanced civilizations elsewhere, but with the twist that they could exist in a dimension parallel to ours, rather than a distant region of space. A truly universal quantum code might be the key. However, most scientists remain skeptical. They point out that even entanglement, incredible as it is, has not been shown to send usable information faster than light or across dimensions. Any attempt to claim otherwise runs into complex mathematical constraints and the risk of mixing science with wishful thinking. While quantum mechanics is undoubtedly strange, it does not automatically justify every far-reaching idea about parallel universes. Still, the imaginative appeal of quantum gateways persists. Our technology is steadily improving, giving rise to more powerful machines and more refined experiments. If unusual data eventually emerges, data that defies every classical and quantum explanation we know, a handful of researchers may look again at the interdimensional messenger hypothesis. Even if such a discovery never materializes, the journey to explore the unknown can lead to new insights about quantum phenomena. In the meantime, quantum computers serve more down-to-earth purposes, like error correction, optimization, and chemical modeling. Yet part of science is dreaming big. The notion that these machines might uncover secrets beyond our own universe inspires researchers, intrigues the public, and reminds us how much we have left to learn. The ethics of the infinite. With great power comes great responsibility, and quantum computing introduces moral questions that society has never encountered before. Once these machines reach maturity, they could break certain forms of encryption, exposing personal data and critical infrastructure to risks. Nations are already rushing to develop quantum-safe cryptography that can withstand such attacks, but the timeline for widespread adoption may lag behind quantum progress. Beyond security, the possibility of a multiverse or interdimensional communication intensifies ethical concerns. Should we attempt to contact or gather resources from other realities, if that becomes possible? Would meddling in alternate timelines create unforeseen dangers? These questions may remain speculative for now, but they highlight how quickly theoretical physics can merge with practical dilemmas once technology catches up. Quantum breakthroughs could also amplify social inequalities. If only a few large institutions or governments have the means to build high-end quantum machines, those groups might gain a huge advantage. This advantage could include not only commercial or scientific leadership, but also the ability to shape policies, set prices, and dominate digital security. Such concentration of power could widen gaps between countries, companies, and social classes. The conversation goes deeper when we reflect on how quantum computing might change our sense of identity or existence. If evidence emerges that we are one branch among many, some people might lose a sense of meaning in their lives, while others might find it liberating. Faith and tradition could be challenged by scientific findings that clash with conventional beliefs. All these shifts call for honest dialogue about where technology and spirituality intersect. Medicine beyond worlds quantum computing has the potential to transform healthcare by tapping into the idea of parallel dimensions, realms that could hold answers to some of our most difficult medical questions. Even though it sounds like science fiction, this concept draws attention to how quantum systems might unlock completely new ways of healing. One key aspect of quantum computing is its ability to process enormous amounts of data at once. This trait could allow researchers to run simulations of complex biological processes in ways that regular computers simply cannot handle in a realistic time frame. Imagine that, in some parallel reality, certain diseases have helped prevent future disasters. A more speculative idea is that quantum computers could offer glimpses of future states. This notion is sometimes attributed to the possibility that certain advanced algorithms, given enough qubits, might effectively sample outcomes of extremely complicated processes. Whether this equates to literally seeing the future is debated, but even partial predictive power has massive implications. Climate scientists, for instance, could predict tipping points with uncanny accuracy, providing a chance to intervene before it is too late. Temporal manipulation of this kind also brings moral and existential issues. If a quantum machine can forecast a likely outcome, and we change our behavior based on that data, do we risk paradoxes like those envisioned in time travel stories? Even if the risk is purely theoretical, the anxiety surrounding altering one's own destiny might creep into public consciousness, possibly causing fear and inaction. Another avenue of exploration is quantum archaeology, a fringe idea suggesting that quantum computers could, in principle, reconstruct entire past events by collecting scattered data that still exist in the universe. Some dream of resurrecting lost information, from extinct languages to long-deceased relatives. However, privacy concerns loom large here, as do questions about the authenticity of these reconstructions. Unlocking the cosmos quantum computing may also help unravel cosmic mysteries that have confounded scientists for generations. Dark matter, dark energy, and the origins of life itself remain some of the biggest unanswered questions in modern science. These areas involve staggering complexities of physics and biology, realms where quantum approaches might reveal hidden layers of truth. Dark matter makes up most of the known matter in the universe, yet it does not interact with light in ways we can detect. Researchers are left guessing its nature based on gravitational effects. Quantum simulations could hypothetically sift through countless theoretical particles and interactions at lightning speed, pinpointing which ones best fit observable data. If alternate universes hold variations of fundamental physics, quantum methods might hint at how dark matter behaves there, providing clues that direct experiments here. Similarly, dark energy, the mysterious force that seems to be accelerating the expansion of the universe, poses an enormous puzzle. Traditional models struggle to integrate dark energy with other known forces. Quantum computers adept at analyzing large-scale interactions could run simulations that classical machines can hardly begin to handle. Even if these simulations do not lead directly to answers, their results might rule out weak theories and push us closer to a unified explanation. Some hypotheses suggest that life emerges under specific chemical and environmental conditions, yet the precise sequence of events remains elusive. Quantum simulations might be able to examine countless variations of these building blocks. If the notion of parallel realities has merit, certain universes might have earlier or easier paths to life, offering hypothetical case studies that scientists here could learn from indirectly. Even in purely classical contexts, quantum algorithms excel at exploring combinatorial problems central to evolutionary biology. Though it all sounds promising, caution is crucial. True breakthroughs will require error-corrected quantum systems capable of handling large-scale tasks. Current quantum machines are still in their infancy. Moreover, any data gleaned about parallel universes or new physics requires validation. Scientists must develop rigorous checks, reproducing results in multiple ways before accepting them as accurate. The ultimate prospect is that quantum physics, supercharged by advanced computations, could open fresh lines of inquiry. Perhaps we will discover entirely new principles that unify gravity with quantum mechanics, or solve riddles about how consciousness arises. Maybe we will confirm or refute the presence of a multiverse. In any case, quantum computing's ability to handle data in out-of-the-ordinary ways stands to deepen our engagement with the cosmos. Whether exploring new forms of life, explaining cosmic expansion, or illuminating hidden aspects of matter, quantum computing reimagines the boundaries of human knowledge. It is a reminder that existence might be more layered, interconnected, and full of surprises than we can currently conceive. While each success will likely raise new questions, That cycle of discovery drives us forward, revealing the universe as a place larger and stranger than we ever dared to believe. Armies of the future. As quantum computers show the promise of performing massive calculations at unprecedented speeds, governments worldwide are racing to harness their power. Military strategists see the potential for quantum technology to reshape national security, leading some to call this trend the quantum arms race. While research in quantum computing remains in its early phases, real concerns exist about how such systems could be used to gain an edge in defense and warfare. One key worry centers on encryption. Today's secure communications often rely on cryptographic methods that are expected to become vulnerable once quantum computers reach a certain level of sophistication. In theory, a single high-powered quantum machine could crack codes that would stump even the world's fastest classical supercomputers. Nations and major organizations are therefore investing heavily in quantum-safe encryption, worried that any delay could leave them exposed to cyber attacks. Beyond cryptography, militaries hope to use quantum computing for rapid data analysis on the battlefield. With algorithms capable of sifting through huge amounts of sensor and intelligence data, quantum systems might detect patterns or threats that traditional computers cannot see quickly enough. These applications could lead to more effective drone coordination, better missile defense, or improved simulations of complex mission scenarios. Some also imagine quantum-based decision aids, where an advanced AI harnesses quantum processors to generate tactics across endless possible battle outcomes. However, these developments raise urgent ethical and geopolitical questions. If a single nation achieves a major quantum breakthrough first, others might feel alarmed or forced to respond aggressively. Countries may pour even more resources into quantum labs, intensifying global tension. At the same time, lesser-known actors might seek to exploit vulnerabilities if they acquire or steal quantum technology. The result could be a new arms race, where secrecy, espionage, and mistrust overshadow international cooperation. Perhaps the greatest challenge is ensuring that quantum breakthroughs benefit humanity, rather than driving it toward conflict. If nations invest in research while also agreeing on guidelines for responsible use, quantum technology could serve peaceful goals. Earthquake forecasting, climate modeling, and medical research might flourish. Yet, if political competition dominates, the world risks turning quantum discovery into another tool of rivalry, with consequences that may be felt for generations. Quantum computing may not confirm or deny the existence of endless worlds anytime soon, but it has widened the conversation. These ongoing debates remind us that progress in science often leads us to reflect on the grand scale of being. In grappling with the multiverse, we confront the possibility that our reality is bigger and more layered than anyone ever imagined, and this alone can shift our perspective on who we are and what lies ahead.